As we talked first about reactions, then connected it to stoichiometry, the idea of being aqueous in a net ionic equation and using molarity in stoichiometry equations came up multiple times. When we have a solution, most solutions will deal with our aqueous. But as we talk about intermolecular attractions, we'll see there are other possibilities, but really this is our focus. When you are trying to measure how much stuff is dissolved in a solution, there's lots of different ways you can do it. Percent, or for smaller things, parts per million or billion. But in chemistry, and especially in AP chemistry, we focus on molarity because it connects moles to volume in terms of liters. Those are the quantities that we want and we need. And we already did some math with those. You can use this as an equation, or depending how you're looking at it in a stoichiometry problem, you can set it up as a conversion factor. But when we're thinking about that, we remind ourselves that we're talking about a solution. So the whole volume is our solution together. The molarity is telling us what's in there. It is telling us how much solute, or the thing that gets dissolved, is in our solvent. So we normally, and with aqueous, always are dissolving in water. So the volume there is the total of both of them together. The moles is the stuff that we put into it. It could be a solid, a liquid, or a gas that we put into there, but we're knowing it or thinking about it in terms of moles. We could put very little and have a watered down or dilute solution, or when a whole bunch, or when a relatively high amount of solutes there, we call that concentrated. We could think about it as strong versus weak for coffee, but that's not the same thing as strong and weak in terms of dissociation. At a certain point, when we add more and more either solid or even a gas in there, no more can be dissolved. It has reached its maximum amount that can be dissolved. It's saturated, and that maximum amount is called the solubility. It has to do with how strong the attractions are between the particles, because we have to overcome attractions, we have to make attractions, and that's what keeps things dissolved. When we are making these, we can make them with any state, as I said. Solid will kind of be the most common that we think about. But if we are actually creating this, it's important that we understand the process. It's a process we'll do in experiments. It's a process that you'll see questions about. And in this process, maybe the most important thing is understanding the precise glassware. There is a special piece of glassware called a volumetric flask. So it looks more or less like this, a big bulb on the bottom and a long, skinny, fairly fragile neck. It's called volumetric, because it's precisely made to measure a volume to a certain degree of precision or a certain number of significant figures. So they're made to mix, they're made to measure, and it's important that we know how and when to use them. So the first thing we do is we put some water in there. That has to do with safety, because a lot of times dissolving things releases heat. So having the water in there first keeps us a little bit safer. Then we would think about how much solid is needed. Well, we know our total volume. We know maybe the molarity we're going for. So we calculate our moles. We think of that in grams, and we measure it out and transfer it in. We're careful to make sure it all gets transferred in. And if we measure it on a weighing dish, we might rinse that weighing dish to make sure that it all goes in. That would be a source of error if we did not do that. In terms of the volume here, a volumetric flask is always defined by a certain volume. We have flasks that are 50 milliliters in size, 100 milliliters in size, 200, 250, 500, 1,000, 2,000. So the volume itself is defined by the flask. The molarity is usually our target. So then that's how and why we know the moles. After we've done that, we see, okay, I've got my stuff in there. Often we mix that up. We shake it a little bit. We might put our lid on there even at that point. And then we add more water. We didn't fill it all the way up with water and then add our solid, because it might go over the line. We didn't put our solid in first and then add up water. And we didn't, with this, let's say this is 250 milliliters, we didn't measure out 250 milliliters, put in 125, and put in 125 because the stuff that we put in took up space by itself. Liquid volumes aren't always conserved when we're mixing stuff up because of some differences in IMFs and the size of particles when they're dissolved versus not dissolved. So therefore, if I want exactly 250 milliliters of solution, we have to do kind of this Oreo method: water, filling, water. And then once we're perfectly at the line, we know we've made the solution exactly as it should be made. If we aren't making the solution from a solid, we might be making it from another solution that we already have. Our chemical storeroom is full of solids of all different types and all different reactivities, but there's also a lot of solutions that we call stock solutions, or chemicals that we buy at a certain molarity that we either use at that molarity or we can use to make other solutions. For hydrochloric acid, for example, we can buy it as 12 molar, 6 molar, 3 molar, 1 molar, and 0.1 molar. But if we need anything in between any of those or below that, we would have to take one of those solutions and water it down. By watering down maybe a 12 molar solution, I could make a 9 or a 5 or a 4 molar by having the right ratio of solute to solvent for the final molarity. When we're doing this, this equation right here is often called the dilution equation. It's not given, but it's just based upon the definition of molarity. Molarity times volume gives me moles. And as I'm adding water, I'm not changing the moles. So I'm still, the moles before my dilution and the moles after my dilution are the same. When we do this, it would be the exact same process. We would add water, we would add our stock solution, we would add water. So water, stock, and then water process, both for safety and precision. We always make solutions in volumetric flasks. We don't do this in beakers. We don't do it in Erlenmeyer flasks, and we want the most precise measuring tools as possible. And even when we're mixing 50 milliliters of one liquid and 50 milliliters of another, we can't assume that that will come out 100 because of the way the intermolecular forces might be different by the time they mix. So we always use the water, mixture water, and fill to the line. So making solutions is a process we'll practice, and it's a fairly common question you're asked to describe how to do on an AP free response question.